Rolling is nothing but rotation and translation rolled together. So you take an object which is rotating in place, the hub is fixed. Take the same object, translate the hub without any rotation, add these two motions equal to, you get rolling. And the object basically rolls as we find intuitively appealing. So what is this? How do we describe this mathematically? First look at rotation. Suppose there is this wheel. Now this wheel rotates into the plane of the board. The way I am going to rotate my pictures is actually the other way. I hope you don't get confused. That is because I want my rotation to be along the z axis of this picture. So consider this wheel. They should have drawn a plus, but then the picture will get too messy. So I have just drawn the rim of the wheel. This is the point C of contact between the rim and the floor, and here is x, here is y, z is coming out of the plane of the board. This is the situation of the wheel at time t. At time t, this one spoke alone is joining the hub of the wheel to the point of contact C. Now let us consider a time t plus dt, a small incremental time away. So point C has moved to point C dash because the whole wheel is rotating out of the plane of the board. My thumb is pointing away from the plane of the board. So if I do this, then C goes to C dash. This angle through which this radius, this spoke R rotates, is called d phi. This scalar angular velocity is defined as d phi dt about the z axis. Hopefully you have seen this before in a physics course in high school. So omega is d phi by dt, rate of change of angle with respect to time, rate of change of angle that a spoke makes in this picture with the vertical with time. This angular velocity is actually not a scalar because we keep showing our hand like this. So it has a direction, and so it should be appropriately described as a vector only. It is having a magnitude which is that much, but it is also having a direction. It is not rotating about some other, each of these would be different angular velocities. So because it has a direction, we write it as a vector. Its magnitude is this much, and the sense of rotation is given by the right hand thumb rule. So it points away from the plane of the board. It's along the k hat direction. K hat is this unit vector along the z direction. So angular velocity is actually a direction. So now let us consider the position of C with time if this creature angular velocity is actually a constant. The wheel hub is fixed. So in this picture we are talking not about this condition of rolling, we are talking about this rotation still, right? We will come to translation, then we will add like this video shows and do all that later, but for now we are only considering rotation with the hub fixed as in here. And if omega is a constant, then any point C, its position relative to x, y, z can be written like this, that angle is omega t. Then you have so the position of C dash, its x component is r cos omega t I hat being along the x axis, plus r sin omega t along j hat being along the y axis. With all that, the velocity is simply the rate of change of position with respect to time. You go ahead and differentiate this. Note that I hat and j hat are not functions of time, they are constants, and you will get this quantity. So you will get velocity of C dash is minus omega r sin omega t I hat minus cos omega t j hat. If you substitute t is equal to 0, which corresponds to finding the velocity when the radius is exactly vertical, then you get the velocity of C dash at t is equal to 0 is omega r times j hat. So, velocity is pointing this way. In this picture, omega is pointing going this way, which is opposite of what it is doing in this video. Okay, that is because I want my omega to have a positive k hat in this description, otherwise I have to carry a minus k hat throughout this derivation. So, what we see is that if omega k hat is the angular velocity of a solid, then the point of contact has a velocity which is tangential to the wheel and it is pointing this way. So, this is the linear velocity of C. Omega is the angular velocity of the wheel, omega r j hat is the linear velocity of the point of contact. Now, in what way is this point special? There in no way is it special. So, I happen to draw this line vertically downward, but I could have drawn it this way also, or this way going up, or this way, or any which way. Whichever way I draw it, if I had drawn it this way, just because I got this velocity at C, over here I should get that velocity, over there I should get that velocity, over here I should get this velocity, and so on and so forth. That is what I have drawn here. If I were to consider my C here, and I did, then I got this velocity. If I took this to be my C, I should get that velocity. The vectors change, but basically the idea is that if omega is the angular velocity, each of the points on the circumference is moving tangentially in a direction that is consistent with the sense of omega, and each of their velocities has to be the same. So, this is kind of a messy description. If you go here, it is j hat. If you go to that point, it is minus I hat. If you go to that point, it is minus j hat. This is plus I hat. If you take some other position like this and try to calculate its velocity, that will have both I hat and j hat components. On the whole, the entire picture is description in terms of Cartesian I hat, j hat and all is extremely complicated. There is a certain simplicity to this picture. Tangential velocity is constant, its magnitude is r omega, that is all. But what we have to do is write I hats and j hats and so forth. So, to avoid this confusion, this mess, it is better to describe the velocity in polar coordinates. So, polar coordinates are coordinates which have er and e theta. Er is the radially outward direction, e theta is the tangentially outward direction. So, if you look at this place, er and e theta are pointed like this, here er and e theta are like that, everywhere er and e theta is along the radial and tangential direction relative to the center, which in our case coincides with the hub. So, in polar coordinates, we can write the velocity more simply. We say that v vector equal to r omega times e theta hat. This is the description of the velocity anywhere on the circumference of this solid. So far we have talked about rotation. So, rotation is the first component of rolling. We have talked about rolling, rotation, and we have found that if omega k hat is the angular velocity of the rotation, then the linear velocity of points on the circumference of the circle of the wheel is given by this formula in polar coordinates. Now we talk about translation, which is considerably simpler. Translation is simply dragging the wheel from left to right so that all the points are moving at constant velocity. So, the linear velocity of every point is actually Vj hat. It is more convenient to write translation in terms of I hat and j hat, which do not rotate. They are not, it is to use polar coordinates here will be very messy. So, there are two different things, and together rotation plus translation produces rolling. So, let us go back to our original picture of rotation. This is rotation. We have here omega being the constant angular velocity of the wheel, and as you can see, all the linear velocities of points on the circle are r omega going that way. If you consider translation on the other hand, here is this v, and every point on the wheel, whether it is hub or circumference or whatever it is, moves to the right with v. And so what happens if you add these two types of motion together is you are actually adding the velocities together. So at the bottom you have r omega plus v, at the top you have v going this way and r omega that way, so it is v minus r omega, and here it is some other crazy direction which is a sum of this vector and that vector. Here it is the opposite, which is the sum of those two vectors. So rotation plus translation in general is gives you a velocity distribution around the circumference like so. Now, of all rotations and translations, you can superpose any rotation with any translation and get yourself a velocity distribution. Nobody stops you, but one of those is special, and that special thing is called pure rolling. So this is simply the same picture that I drew in the previous slide. So the condition of pure rolling, remember, this is completely driven by omega, there is no v here. This is completely driven by v, translation is driven by v, rotation is driven by omega. Together they give you v plus r omega speed at the bottom. So if v and omega, instead of being unrelated like they are here, if they are related through this equation, which gives you zero speed at the point of contact, that is called pure rolling. So when v and r omega obey this equation, v plus r omega equal to 0, then you have zero speed at the point of contact, and that corresponds to rolling. And what we see in this video over here is actually pure rolling. So it's very hard for you to infer by looking at the video. The point of contact is actually not having any relative velocity to the substrate, but you should think about it like this. Suppose your bicycle or car or whatever it is was having velocity relative to the road when the vehicle is moving, then it would just wear out extremely fast, right? If you were to take a tire and just rub it all over the surface of the road, that's what happens when you apply emergency brakes. So, and that will produce this burning rubber smell, and you know that you have basically slipped the wheel on the road. Whereas tires actually last quite long, and they last so long because instantly at the point of contact, not here, the point of contact actually does not move relative to the road when it is rolling, and that is how that is why you are not supposed to brake suddenly and skid the car or skid the motorcycle or skid the skidding a cycle is kind of hard, but skid any tires on the road to make them last long. So in the condition of pure rolling, omega equal to minus v by r. We happen to get minus because the rotation actually has to follow this path, the translation has to follow this path, and these two effectively oppose each other to produce zero velocity at the point of contact. So in pure rolling, this is the velocity profile. The point of contact actually has zero velocity. The topmost point has the greatest velocity, linear velocity, relative to the ground. So we have two special cases that we should consider. Here again we come back to our good old preoccupation, which is the direction of friction. The direction of friction depends on which way. Direction of friction basically depends on the direction of impending motion. So let us consider two special cases. So we have omega equal to v by r. If you had omega equal to v by r and translation happening with speed v, let me write that down. if you have exactly omega equal to v by r and translation happening at speed v, then you have a condition of pure rolling. Now suppose we have a little faster rotation than what is required for pure rolling. Suppose instead of v by r, which will give you pure rolling, we have v by r plus delta omega, which is going to give you, so basically rotation is a little bit faster. So this point is moving this way according to rotation, it is moving this way according to translation. So there is a net backward extra velocity of this point. There is a little backward extra velocity. If you add this v and this velocity and that velocity, the v's basically cancel, and what is left out is this delta omega into r, which is acting this way. So friction has to oppose motion, relative motion, so friction will act to the right. Why? Because relative motion is to the left. So friction will apply a moment on this wheel which will be to the right, and that will actually slow down the angular velocity of the wheel. So essentially what friction does is it tries to push the wheel toward pure rolling. So we have a condition where pure rolling is being violated, and just by its action friction makes the wheel go toward pure rolling. So friction is a very stabilizing force, but for friction almost all vehicles would be uncontrollable. They will just move any which way on the road. It will be like if you are driving a motorcycle on a snowy road with very little friction, on an icy road with very little friction, it is extremely hard to control the motorcycle. It will skid this way and that, and you are very liable to fall down. But when it is in full force, when it is in full action, friction tries to push the wheels toward the condition of pure rolling, and in the condition of pure rolling, where the point of contact between road and tire is actually at zero speed, the vehicle is very controllable. It will go where you tell it to go. So this is one case where the wheel wants to rotate faster than it should for pure rolling. So suppose the wheel wants to rotate slower than it should for pure rolling. Suppose the wheel is rotating slowly, then again we have over here translation with v, and at the point of contact the wheel is actually having a forward, a effective net velocity, right? This v and that v cancel if you add these two cases. There is a minus omega delta r backward, which is the same as a plus delta omega r forward. Friction as usual opposes relative motion, acts backward, and by acting backward, friction is actually trying to spin up the wheel. So if you take this wheel and you rotate it this way, then friction is spinning up the wheel, and it is essentially pushing the wheel once again toward pure rolling. So this is friction acting as a very stabilizing influence and making our vehicles safe and controllable. So friction has a stabilizing effect on rolling wheels. If the angular velocity is incompatible with the linear velocity of translation, friction forces or modifies or changes the angular velocity so that the motion of the wheel approaches pure rolling. An example of this is the case where a plane lands. So when the plane is up in the air and is approaching the runway, the landing gear, both nose landing gear and the main landing gear, the wheels are not rotating, and so that corresponds to roughly this case where there is a large V, but omega is actually 0. In fact, delta omega is equal to V by R, so that there is no rotation of the wheel at all. And when the plane does touch down, when the wheel does touch down, you see this large puff of dust and water in this example being released by the main landing gear, and a somewhat smaller puff being released by the nose wheel, simply because as a signature of friction kicking in and revving up the wheels sufficiently to produce a lot of angular velocity there, so that all the wheels basically go into a condition of pure rolling.